Let's start off our concepts with just a little Amazon networking refresher. Now, you should already know the physical layouts of an AZ and the region concept. You should know what a VPC is and how to create one. You should be able to create private and public subnets and know what the difference is between the two. You should know what NAT is and what disable source destination checks mean. You should know what a routing table is and some basic routing terminology like default routes and local routes. You should really know your IPv4 addressing and subnet mask notation. So /16 should mean something to you and /24, and you should know what that means in terms of a net mask. For the exam, don't worry too much about IPv6, but you really should know IPv4. And you should also know some intermediate networking terminology like what a MAC address is, what a port is. You should know the difference between a gateway and a router. So you hungry yet? I sure do love me some pizza. And feel free to go grab something to eat while you're watching this chapter. If you don't have much of a background in networking, this might be a pretty challenging chapter, so your brain could probably use some extra energy. And the objective isn't to make you a network engineer, but just to give you enough vocabulary and concepts that the AWS networking features make sense. And remember, we seek first to understand, then apply. Speaking of understanding first, I'm going to introduce you to something that has really helped me, and that's the OSI model. If you want to really impress your network engineering buddies, learn the OSI model. Way back when I was studying for my very first certification, the coveted, at least at that time, it was coveted, Certified Novell Engineer, I had to learn the OSI model. And it describes how to think about network operations. If one layer has a problem, then your message isn't going to get through. Your web browser is not going to receive that web page, or that ill-advised tweet after a night of partying never goes out. It's also quite helpful in troubleshooting networking and application problems. I use it as sort of a mental checklist when my network isn't working quite the way I want to. And so it starts at the very bottom. That's the physical layer. That's the copper or the fiber optic cable that carries the signals. Now we have the data layer, and that's the MAC address layer. That's the layer of your network card, and the hardware of that network card is assigned its MAC address, which is its unique identifier. Then we have layer 3, which is the network layer, and generally protocols like IP or IPX or ARP live on this layer. Then we have the transport layer. This is where TCP lives. The session layer, we have the presentation layer, and ultimately we have the web browser at the application layer. And that interprets the messages coming across in the HTTP protocol and renders that as HTML so you can see the web page. The reason I had a pizza on the previous screen is because there's this mnemonic that helped me remember the layers of the OSI model, and I still remember it to this day. It's please do not throw sausage pizza away. Now, the reason I have a yellow line here between layers 2 and 3 are that's kind of a general point of demarcation between what AWS's responsibility is and what our customer responsibility is. So if you recall from earlier study on AWS, a commonly used term is the shared responsibility model. And in networking terms, the line between customer responsibility and AWS responsibility lies somewhere around the border between layer 2 and layer 3. I say around because there are some cases where both the customer and AWS have the ability to reach across that line. Now, your EC2 instances do have access to virtual items that would normally live at layer 1 and layer 2. An Elastic Network Interface is an example of such a thing, but it's not a physical network card. It's a virtual card that lives in software. And since AWS is a multi-tenant system, they have to be sure that customers can't negatively impact other customers where they're sharing that same physical layer. And so AWS has imparted certain limitations and restrictions. One of the limitations that AWS and most other cloud providers enact is to not allow multicast. Now, let's take a look at the difference between unicast and multicast. Unicast is like a phone call to someone. You dial the phone number, and when the other party answers, you can have a conversation, and it doesn't much bother anyone else on the network. Think about it as like a direct conversation between two people. That's what unicast is. Now, multicast, on the other hand, is like somebody shouting over a loudspeaker to everyone. Kind of like that scene in the classic Blues Brothers movies where they're driving through the neighborhoods with that loudspeaker strapped to their car, advertising their blues show that night. And this is why AWS doesn't allow multicast. You see, multicast is when a network card starts sending messages to everybody on the network. And because this is done at the MAC address level, it's a layer 2 activity. So if AWS allowed multicast, then it could negatively impact other customers' network activities as well. So a key thing to remember here is that multicast just doesn't fly on VPC officially. Now, there are some third parties that have come up with workarounds, but in the context of the exam, multicast isn't supported. Let's take a look at the differences between 3 layer 4 protocols, and you're probably going to get asked some questions on the exam regarding these protocols. First, we have TCP, and TCP is known as a connection-based stateful protocol, and it acknowledges receipt. So in plain speak, after everything I say, I want you to confirm that you received it. In contrast, UDP is connectionless and stateless. The plain speak version of that is, I'm going to start talking, and it's okay if you miss some words. UDP is used in streaming media applications and also in DNS, mainly in DNS because it's very simple, and streaming applications because it doesn't require an acknowledgement for every packet of information sent. Now, ICMP is kind of like the metadata language of the network. It's generally used by network devices to exchange information. And in plain speak, it would be something like, we routers can keep in touch about the health of our network using our own language. And ICMP is used in commands like a traceroute or a ping. Let's move on to ephemeral ports. So ephemeral ports are these short-lived transport protocol ports that are used in IP communications, and they generally exist above what's considered the well-known IP ports, meaning above 1024. And they're also sometimes called dynamic ports. And the suggested range for them to live in is between 49.152 and 655.35, but different OSs have different default settings for ephemeral ports, so be sure to double check your OS for whatever the default ephemeral ports are. Now, they definitely have some NACL and security group implications. And so let's look at how ephemeral ports work and why they work. And I think you can see why they do have these implications on our security groups and NACLs. Now, this is a quite simplified example, but this is just to give you an idea of the type of conversation that goes on. And in this case, we're using TCP. So there's a connection that's made, and there's also some TTL, time to live, that we're going to have to keep in mind as well. And this concept will come into play more prominently when we start talking about elastic load balancers and something called sticky sessions. So in this case, let's just say we have a web server here that's on the left. It's just hanging out, listening to port 80. And then we have a client. And that client dials up the IP address of the web server. And it says, hey, I'm client 6, and use port 56784 to respond to me. So this is an important concept because the client is in charge of defining the ephemeral port that the server should talk back to on. And so the server says, hello, this is server. Nice to meet you, client 6. Here is your web page, and I'll keep a session open for you, and it's going to respond back using port 56784. And the client says, thank you, sir. So it acknowledges that it received that message. Remember, we're talking TCP here, so there's an acknowledgement. Then some time goes by, and the client says, here's another web page, and it's going to communicate on port 80. And the server says, hey, I know you. I'm going to use the existing session that I already have open. And because I already have that session open, I know that you like to be communicated on 56.784. And of course, the client says, thank you very much. Now let's look at an example that uses both TCP and UDP. So the same scenario happens. The client says, hey, I'm client 6, use port 56784. And let's say in this case, the client is requesting a media file, and it uses UDP for streaming that media file. So the server says, hello, server. Nice to meet you, client 6. Here's the video stream that you requested, and it's using UDP port 56784. And the client doesn't say anything. It just gobbles up the data. And the server sends more, and the client just keeps gobbling up that data. And the server sends more, and so on. And so this is a demonstration of the difference between TCP and UDP. UDP is just send, and the client just consumes it. This is why UDP is favored when we're talking about streaming media, because you can see if you're sending a lot of data, having to acknowledge each and every packet of that data could get very burdensome on the network and on the client and on the server and so forth. So this is how we use UDP. Now, I also wanted to talk about the reserved IP addresses in AWS VPCs. And there are 5 reserved IP addresses that you just can't use. Now, in this case, we're using a subnet of 10.0.0.0/24. So in that particular subnet, the addresses we can't use would be the 0 subnet, that's our network address, the 1 address, which is reserved for the VPC router, the 2 address, which is reserved for the AWS DNS, and 3, which is reserved for some future use that AWS doesn't know yet. And finally, we have the broadcast address, which we can't use as a valid IP address either. Now, keep in mind that it's not these specific numbers that are reserved, rather it's the sequence or the placement in the IP range. So if we look at a different CEDAR block, or CIDR block for you purists, the network address in that case is 16. And that would mean 17, 18, and 19 are unusable for us. And in this case, 31 is the broadcast address of this particular subnet. So when you're architecting your subnets and your VPCs, make sure that you use some ranges that have enough IP addresses that you can account for these addresses that you're unable to use. Now, just a brief note here, something that maybe some people aren't aware of, but the physical to logical assignments of an AZ is done at the account level. So in other words, when your account gets created, the physical availability zones are assigned to their logical names. And that means your US West 2A may be a different physical AZ than another account's US West 2A. And so why does AWS do this? Well, really to balance the load across its data centers. If you're creating a new instance, you're probably going to naturally lean towards dropping that in availability zone A, for example, either consciously or subconsciously. And so by randomly distributing how the logical names line up with their physical counterparts, Amazon hopes to distribute the load there equally. There's a bit of a security angle here too. Let's say you wanted to do harm to a company and you happen to know that that company stored their data in US West 2A. Well, you could go and do something bad to US West 2A if you knew that that US West 2A equated to one and only one physical address. Now, Amazon doesn't publish the exact addresses of their data centers, but I imagine in the communities they exist, they probably stand out a little bit. But using this round-robin distribution, even if you knew that a company stored their data in US West 2A, you'd basically have a 1 in 3 chance of guessing correctly.